EECS 281, lecture number 20, Algorithm Families. Today we're going to discuss some general categories that our algorithms fall into. And there's 6 different families that we'll put forth, and we'll see how many of the algorithms that we've already looked at fall into these categories, and others that we'll see in the future. You'll be able to look at that and see which type of algorithm is this. We have 6 of them: brute force, greedy algorithms. We're going to pair those 2 together. These 6 have a set of pairings in them. They relate to each other. The families do. The next pair is divide and conquer and dynamic programming. And finally, we'll look at backtracking along with branch and bound. A brute force algorithm, by definition, solves a problem in the most simple, direct, or obvious way. It's called brute force not because it's simple, but because it tries everything. A brute force password cracking algorithm, for instance, tries every combination of letters and numbers. And this is one of the ones that we love to see on our movies, and somebody will stick some device in a card reader, for instance, and you'll see it buzz through a bunch of numbers and spit out the password and just before the guard gets around the corner. In reality, those things take so long if you're going to crack a password that has letters, numbers, and non-alphanumeric characters in it, that it's actually measured in years, centuries, not seconds. So brute force algorithms don't have a general structure or a form to the way we set them up. Mostly it's just a bunch of loops. So try this and try that and try all of those things together. Pros are they're often pretty easy to write because you just write a loop that tries everything. It's easy to see what everything is. It's harder to sort of figure out how to do it artfully. So brute force is straightforward and easy to implement. However, it often does much more work than necessary. Can be efficient, but typically it isn't. And even sometimes, as a con, it's hard to figure out how to get that obvious run at every single choice. One example we'll take up here, counting change. So the problem definition is something we're all familiar with. You go to a business and you buy something, you give them currency, and they're going to give you change back, your version of what you didn't spend. So the cashier has this collection of coins. They're in various denominations. And the goal, of course, is to get all of your money back. That's your goal for sure. And then the secondary goal is to make sure that you've got the fewest number of coins in your pocket as possible. Nobody wants to be doing any extra jangling, that's all. So the goal is to get the specified sum back using the fewest number of coins. So here's our mathematical definition of the problem. We've got these n coins, right? And we'll call those p. P sub 1, p sub 2, p sub 3, all the way up to p sub n. Each one of those has a value d associated with it, d sub 1 all the way up to d sub n. And what we can end up with is repetitions. That's fine. Multiple dimes, multiple pennies, nickels, quarters, or whatever. So what we're looking for is some subset S. This is the change subset. The subset of P, which is that I've got this 1 and 0 set up. So if S sub I is 1, that means coin P sub I is included in the change. Right? If S sub I is 0, then that means the coin P sub I is not in the change. That's pretty straightforward. You can open up a drawer and say, for every coin in this drawer, as I give you back your 14 cents, I can tell you this coin is involved in that 14 cents, and these coins are not. So that's pretty simple. So in the end, we want the sum to be returned, which is the D's of all of those coins. That has to be A, the sum that we're trying to get back, the customer's 14 cents or whatever it is. And then the other goal is to really minimize the total number of the ones that we've added up. Because remember, there's a 1 for every coin that's included, and all the coins that are not included are 0. So we want a minimum S and exact change A. The brute force approach. We'll just try all subsets of P. This we know is the power set. All subsets of P. Since there's these n coins, and every coin can either be in a change set, 1, or out of a change set, 0, then we can say for every coin, there's 2 choices. It's in or out. And then I can multiply all those choices together for each coin. 2 coins have 2 options each, so there's 4 different ways I can make that change. Both coins out, both coins in, 1 coin in and the other coin out, and vice versa. So as I go on and add additional coins, I get to that 3rd coin. Now there's 8 ways I can make change with 3 coins. That's me going exponential, 2 to the n. So as I enumerate all these possible subsets, now I've got some work to do. First, I need to figure out if the subset is a legal change set. I mean, if somebody says I'm supposed to get 14 cents back and they give me 3 cents, that's not going to make me happy, right? And conversely, if somebody says they owe me 14 cents and they give me 97 cents back, their boss isn't going to be happy. So someone's not going to be happy as long as our subset, the D's, don't add up to A. We check that. And then once we've got that, we say, well, this is a feasible solution because it actually accomplishes the primary goal, which is giving you your change back. Then we have to pick some subset out of those feasible solutions that are going to minimize the total number of coins, right? We call that the objective function. So as you look at that, checking to see if a subset equals A. That means I've got to add up all the coins in the subset, which in the worst case could be me adding up all of the coins. That's why we call this one a big O of n, just to see if we've got the right value. Then, simply as well, I got to figure out how many coins are in that list, which I couldn't do easily in the same loop, but it's definitely a big O of n because I could say, well, every coin is in there, and it took me n time to count all n coins. Any fraction of n is still going to look like big O of n. So I can say that I've got this large power set, which has 2 to the n subsets in there. And then for each subset, I got to check to see if it's feasible and check to see if it minimizes S. So let's get 30 cents here. Brute force is going to try them all, and I don't actually have enough room to try all of them on a slide, but I'm going to give you the straightforward ones, right? These are the ones that are going to add up to 30 cents. All of these combinations add up to 30 cents. So in a brute force approach, we don't know ahead of time that we're only going to add up to some 30 cents. We have to take every coin in the drawer and find every combination of every coin in the drawer and then figure out which of those add up to 30. So you can think of the real version of this having a much longer list than just these. These are the ones that add up to exactly 30. And you can see here that the easiest way to get there, and I guess not the easiest way, but the way with the fewest number of coins, right down here at the bottom, which we already knew, add a quarter, add a nickel, 30 cents, 2 coins, problem solved. But brute force, as I mentioned, is going to try everything. Brute force is going to try, how about 1 penny? Is that 30 cents? No. Well, how about this 1 penny? Is that 30 cents? No. How about this 1 penny? Is that 30 cents? Because for every set, you could say, well, all of the other things are out but this coin. And brute force doesn't know. Maybe there's a 30-cent coin, and if it included just that coin, it would be correct. So, as we look at that, we see that this list is far underserving the reality of what brute force search is doing, because brute force search does dozens of 27-cent searches or 27-cent change sets, or dozens of 39-cent change sets, 39-cent change sets. And each one of those, it says, well, is this 30 cents? And then it says, does it have the fewest number of coins as well? So brute force is going to try everything, many things that are not going to be legal here. So we can say that our best case and worst case all end up looking like this n times 2 to the n, right? Remember, I had to spend n amount of time to verify that I was adding up to A and also count the number of change in the set, count the number of coins in the set. And for each one of those that I checked, How many of them were there? Well, there was 2 to the n of them. So if I multiply those together, that'll tell me how many I need, right? So best case, we've got big omega of n times 2 to the n. Worst case, I've got big O of n times 2 to the n, right? It's not going to be less than this, right? That's what this best case is saying. It will not be less than n times 2 to the n. It cannot be. It's brute force. Worst case, it's n times 2 to the n, and I suppose you could also look at that as being average case of big theta n times 2 to the n. All right, how about greedy algorithms? A greedy algorithm is one that makes a sequence of decisions, and every time it makes a decision, it says, I'm going to take the best at the time. Right now, I'm going to take what's the current best I can do. So if I'm trying to get some distance, for instance, I'm going to take at every chance to make a decision, I'm going to take the one that gets me the farthest that time. Right? It never reconsiders decisions, and it never plans ahead. Right? If it says, well, if I take 2 short steps, I can get a really long step that I would miss if I took a long step now. Greedy doesn't do that because it takes the current best available, regardless of how that affects things later. So you can see how that sort of behavior in real life would often lead to sometimes suboptimal solutions. Right? So in the end, you'd like to be able to show that all of these locally optimal decisions add up to a globally optimal solution. The good news is greedy algorithms run generally much faster than brute force algorithms. Right? Because there's a lot of choices that we don't have the chance to take when we're being greedy. We have to take the optimal or one of the optimal decisions at the time. So in the case of making change, I cannot select a penny when there's quarters available if the change I'm making is still above 25 cents. You absolutely have to check only one of the quarters. The cons, unfortunately, as much as we like greedy algorithms, are really nice and easy to come up with usually. You just take the best at the time, and it's usually a pretty straightforward thing to see when you're solving a problem. However, this doesn't always lead us to the optimal solution, a globally optimal solution. That's what's unfortunate about it. So in the greedy approach to making change, what I'm going to do is go from the largest to smallest denomination, and I return the largest coin whose value is less than the change that needs to be made. And then I subtract that coin's value from the change that needs to be made, and repeat. One thing that this really needs, however, though, is my money sorted. Have to have the things sorted by value. If they are, then all I have to do is look at every single coin and decide whether that coin is in or not. That's pretty straightforward, right? So in the worst case, if I start out with a bucket of change, I might have to do an n log n to sort things, and then I can do a linear, greedy approach to making that change, and I would end up with something that looks like n log n. So that's a lot better than n times 2 to the n. So here we go. This is a greedy approach, and this is the one that you probably learned when you learned to make change. Right? If I'm trying to make this 30 cents, I say, well, let's take the largest coin available. Can I take a 25? Yeah, I'll always pick a quarter if it's less than the change I'm trying to make, until I get down to the point where the change I'm trying to make is less than 25 cents. In that case, then I'll start picking dimes as long as I can pick dimes. And then once I can't pick dimes anymore, I pick nickels and pennies and so on. Right? So what this means then is with the greedy approach, I get one way to do this. That's it. It's pretty fast too. Right? I end up with one possible type of set. So in this case, if I were to sort of look at this in a 1-0 sort of way, I might try a bunch of different quarters with a bunch of different nickels. So it's not to say that there aren't multiple ways to make 30 cents, right? In terms of having this 1975 quarter and this 1982 nickel and so on and so on. But you can see here that with the greedy approach, there's only one way to make 30 cents. You take the quarter first. You can't take a dime because there's only 5 cents left. You take a nickel, there's 30 cents, and you don't have the chance to take any pennies. So here's our one possible solution, and that's why greedy is faster. And we can see here that this is the way we learn to make change. It's actually because of the way that we have our coins chosen, it is globally optimal. So the question here, that's usually an exercise question in class, is can you devise a set of coins and a value for which the greedy approach does not yield an optimal solution? So you can pick the availability of coins, you can pick the value of coins, and you can pick the total amount we're trying to add up to. We're trying to figure out how we can break greedy, right? Because greedy change making is currently optimal because of the way that we choose our denominations, right? So probably the most common one I get in class is what's the most common one I get in class? I'm just drawing a blank here. All right, well, think about it. Think of a value that you can come up with and something that makes it hard to get there with normal coins or easy to get there with an alternate coin. What do you come up with? All right, let's say that we are going to drop out a coin here and see if we can't get to something like 14 cents. Right? So my target then is 14, and the coins that I have are 25s, 10s, no nickels now, 7s, and 1s. So I do that, and I approach this from a greedy standpoint. I'll say, well, I can't make a 25 fit under 14, but I can make a 10 fit under there. So I get one of these coins. Now all I have left to make is 4 cents. I can't do that with a 7, so I'll add 4 of these things for a total of 5 coins. 1 dime and 4 pennies gets me 14 cents. But if I had a 7-cent coin, then what I would end up with a non-greedy approach is I would look ahead and see, well, you know what? It would be smarter if I just used 2 7-cent coins, right? 2 7-cent coins would give me 14, and it would give me fewer coins. So this is a situation where greedy doesn't yield an optimal solution. You say, well, that's kind of odd. Who would pick a 7-cent coin? True, that's a strange way to make change, or to make currency, I should say. But what does happen sometimes when you go someplace and they're out of a particular coin, right? What happens when they're out of a particular coin? You can see that this would also sort of change that. So if I'm trying to make this 30 cents, just go back to our original example. Say I'm trying to make 30 cents and my drawer is out of nickels. How many coins do I choose? I choose a quarter and 5 pennies. And that's 6 coins. Whereas a non-greedy approach would look ahead and say, well, if I choose this quarter, it's going to prevent me in the future from picking dimes. But if I pick 3 dimes now, I'll get to 30 cents with fewer coins than a quarter and 5 pennies. So the greedy approach works when we've got enough coins, and we've got enough of the right coins as well. That's why you see how most of our money goes along these 1s, 2s, 5s, 10s, and multiples of that, right? 1s, 2s, and 5s really sort of break things down. So you like the $1 bill, the $2 bill, the $5 bill. This is in US currency. Then our next bill is the $10 bill, which is just 2 times a $5 bill. After that, we've got a $20 bill, which is 2 times a $10 bill. And we've got 50s, which is 5 times a 10, and hundreds, which is then again 10 times a 10. So we end up with this family of bills and coins that allow us to use the greedy approach and always give optimal change. So here's my example, as I mentioned. Fewest coins that sum up to 30. If I'm missing nickels, then I'm not going to show up with my best change for 30 cents if I use the greedy approach. All right, how about another example? Enough with the change. How about sorting? I'll start out with this precondition that says I've got some random array of ints, and my postcondition that says for all I and j, if I is less than j, then what's at I is less than or equal to what's at j in the array. All right, there's my definition, precondition from sorting and postcondition from sorting. In brute force, we do something that we like to call monkey sort. Monkey sort generates all the permutations of an array. Now, how many permutations are there? Well, at every position, I can pick, at the first position, I can pick n items. At the second position, I can pick n minus 1 items, then n minus 2 items, and so on. I multiply those all together and end up with n factorial. And why do we call it monkey sort? Because I have a monkey sort this deck of cards for me. I give it to the monkey throws the cards up in the air, and then we pick up the cards. Are they sorted? Nope. Give them back to the monkey. Throws them up in the air. Are they sorted? Nope. We keep doing that, and that's going to take quite some time. 52 factorial throws, that's if we don't have any repeat orderings, because a monkey sort is not very optimal. But you can see how sorting by brute force becomes untenable pretty quick, right? Because once I've got that n factorial, I've checked each one of those I've generated each one of those n factorial permutations, I still have to verify whether the permutation is a solution. And remember from our definition here, the postcondition of I and j such that I is less than j for all I and j, then I can say that what's at I is less than at j. To check that ends up being big O n squared. So now I've got each one of these permutations that's going to cost me that much work to get done. So say, well, n squared, who would take n squared to determine whether or not a list was sorted? Well, we pass this, right? So for this version of the postcondition, this is an n squared check, because it says for every I and for every j, I need to make sure that I is less than j. Maybe a smarter version of this, for all I would maybe say if my array at I is less than or equal to my array at I plus 1, now that's a check I can do in linear time. So I can make this a little faster than n squared times n factorial, but not much. I can make it a factor of n faster. I can end up with n times n factorial. That sounds terrible. How about the greedy approach to sorting? Well, the greedy approach is let's get this done the best we can. So if I'm trying to put things in order, I would go for the smallest thing first. Let me go get that and put it into place. Next step, I'll find the next smallest thing remaining and put it into place. Next step, I go greedy. I find, well, I've got the 2 smallest things. I just need to go get the smallest thing remaining and put it into place. That would work. That's a greedy sort. What sort is that? Oh, yeah. That's selection sort. Selection sort is greedy. Selection sort is optimal. It is an optimal solution for sorting. Now, there's faster ways to do it. It's optimal in the sense that I do not end up, you remember when we're talking about a greedy algorithm, the greedy algorithm puts a bunch of locally optimal decisions together and hopes for a globally optimal result, right? So a globally optimal result that I'm speaking of in this case is an actually sorted list. So if our selection sort was not an optimal greedy algorithm, then after I made all of these picks, I would still end up with a list that wasn't sorted. If I do selection sort properly, I will end up with a sorted list. So it is a globally optimal algorithm. There are, however, more efficient algorithms, but this is still a globally optimal algorithm. So be aware of that. All right, let's change our venue again. Let's go mountain climbing. Brute force. How do we look at a brute force mountain climbing approach here? What I'm trying to do in this mountain climbing thing is, I want to get to the toppest point, the highest point on the planet. To get to the highest point on the planet, you have to climb the highest mountain. Sure. Brute force, however, says, let's take the entire planet and divide it up into, say, 1 by 1 meter grids, and then I'll go stand in every single one of those. Once I've done that, I will be certain to have climbed to the highest point on the planet. It's a lot of travel. You get some frequent flyer miles off of that like you would not believe. But you also probably wouldn't get it done in a lifetime. All right. How about the greedy approach? The greedy approach says, well, I'm here, and if I'm trying to get to the highest point on the planet, as long as I can take steps that don't go down, I'm trying to get to the highest place. So I can go from here upwards to the highest place I can see. And once I get there, I'll be able to see more. And if I go from there upwards to the highest place that I can see from there, that's my greedy approach. I'm taking the locally optimal choice, which is get to a higher place than you are right now. So take a step that increases your altitude, repeat until you can't go any higher from where you are. What about these two solutions? We can see that the brute force approach will definitely get us to the highest place on Earth because we'll have been everywhere. So we have to, by definition, have been at the highest place on Earth. So brute force, and it's important to note, is that brute force always finds a solution. It always finds an optimal solution, right? However, greedy algorithms, in this particular instance, you can see how if I get to a sort of a local peak, then the next step I take has to go downwards. Even if I can see a taller peak in the distance, if I can only go up, once I get to a local peak, I've got to go down to get back up later. And greedy approach doesn't allow that. Greedy approach doesn't say, well, I'll allow you to go lower because in the future it's going to let you go even higher. Remember, greedy doesn't look ahead and greedy doesn't look behind. It just takes the best right now and keeps going. So we've got this greedy optimality principle and examples here. When I talk about selection sort, every time I choose the smallest remaining item and put it into place, then my sorted list grows and my unsorted list shrinks. So that's why I can say that eventually this is going to be optimal, because if I was into a situation where I made a choice and after that choice there was a larger number of unsorted items, then I would be not generating an optimal solution. Bubble sort, all of our elementary sorts are greedy, right? Bubble sort just takes 2 items. It says, hey, are these in order? No, then I'll fix it. That's the best I can do right now. I've got these 2 things. So bubble sort is a greedy algorithm. It is also optimal in the sense that when I'm done with bubble sort, I have a true sort. All right? So you can see that when I take these 2 items in a bubble sort and put them in the proper orientation, that doesn't prevent me from getting to a sort later. Every time I do a bubble sort swap, I have removed one more inversion. And every time I remove inversion, I cannot create new inversion. So if I were to make an inversion, remove an inversion and somehow later be able to add additional inversions, then that's a situation where I would not have this greedy optimality principle holding, because you're always looking for when you're saying, is this greedy solution globally optimal, I have to be able to say that I've got no situation where I could have made a worse choice and gotten to something better in the future. All right, enough with the brute force and greedy. Now we're going to move on to the next two families. The next two families are related because they both take a problem and look at it as a smaller problem. So the first one is divide and conquer algorithms. And what they do is they divide a problem solution into two or more smaller problems, preferably of equal size. That keeps things even and fast. They're often recursive, and that makes them often involve log n in terms of their complexity. All right. The pros are they're usually pretty efficient. Divide and conquer is a good way to do a lot of things, even working on your day. Work on this stuff in the morning, work on that stuff in the afternoon. I conquer my morning, then I conquer my afternoon. That's great. They're also usually pretty elegant because they're often recursive, and that elegance is there in quotes just because we know that recursive solutions are often elegant in code, but unless you do them correctly, they are not elegant in time efficiency. So be aware of that. The cons are, when I do these divide and conquer algorithms, I end up with a bunch of calls to small subdomains. So for instance, we looked at quicksort, and in quicksort we found a pivot, and that divided our area to be sorted into two sections, and then I dove into each section. Eventually, though, I never really stopped until I got down to a sort of size 1 or size 0, right? When I had a pivot and there was only one thing to its left, I could say, well, that thing is sorted. Or if there was 0 things to its left or right, I would say, well, that empty list is also trivially sorted. So I had a bunch of calls to quick sort this item of this list of length 1. So that's the con of this recursive version. I'm going to have a lot of these small little sorts. Also, divide and conquer, sometimes dependent upon the initial state of the data. So for instance, binary search is a divide and conquer algorithm. I look in the middle and say, is the thing I'm looking at the thing I'm looking for? If not, I'm going to throw away half of this and go into the other half where I know that the item might be. So that would be a divide and conquer algorithm that we've used, but we know that binary search only works when I've already got sorted data ahead of time. So that's one of the cons. It might be dependent upon a particular divide and conquer algorithm, and these are also, if you look it up in the literature, for some reason D and Q instead of D and C. But divide and conquer, that's the abbreviation for it. So look at a D and Q algorithm, you can see that some of them require the data to be sorted ahead of time. Similar to divide and conquer are combine and conquer algorithms, and they do something similar where they start with the smallest subdomain, then they continue to put things together until we get all of the items in the domain included in the solution. Our quintessential version of that is, of course, merge sort. Merge sort takes these 1-item lists and makes 2-item lists, takes 2 2-item lists and makes 4-item lists, takes 2 4-item lists, makes 8-item lists until we've got everything all sorted. So we can usually think of these from terms of approach. We say the divide and conquer algorithms work from the top down. They take the big thing, make it smaller, make it smaller, make it smaller. And combine and conquers work from the bottom up. They take the small things and make them bigger, make them bigger, make them bigger. So we talk about a few of them. Divide and conquer, of course, is binary search. Quicksort is another divide and conquer algorithm. Combine and conquer starts us right out at merge sort. So you've already seen some of these algorithms, just pointing that out. Next up is dynamic programming. And I said that divide and conquer and dynamic programming families were related because they take the problem to be solved and they make a smaller version of that problem until they can find something easy to solve. So the dynamic programming problems do the same thing. They take a big problem and say, well, if I already knew a solution to a smaller problem, it's easy to make a larger solution. And the distinction between divide and conquer and dynamic programming is when I get a sub-problem in divide and conquer, I get multiple sub-problems when I divide, then those sub-problems are independent of each other. They are non-overlapping. The example given was binary search. When I'm looking for an item and I cut my data section in half, I know that the item is not in both sides. It's in one side or the other, right? It can't be in both. Dynamic programming is different in the fact that I break this problem up into smaller problems, but these smaller problems may not be independent. Okay? And so what I'm going to do is I get this smaller problem and I solve it, and I'm just going to just remember that. I'm going to write it down. I'm going to store it. Then the next time I need that smaller problem solved, rather than doing the work to solve it, I'm going to go look up and say, hey, have I already solved this problem? Because if I've already solved this problem, I'm just going to use the answer that I got from before, and I'm not going to recalculate. Then I can take those smaller solutions and make them bigger solutions. So if I find the best way to do something after 5 tries, then it's pretty easy to figure out how the best way to do something after 6 tries, and the best way to do something after 7 tries. And so that's kind of how dynamic programming works. We solve these small instances first, store the results, and then look them up as opposed to calculating them whenever possible. What this does is great for time complexity. It can take some really, really inefficient algorithms and take something that's exponential and turn it into a polynomial thing here. So you see the example says I can take something that's 2 to the n and end up with something that's n to the c. Like I take something that's exponential and turn that into quadratic or cubic, and that's amazing because it's just so fast. The primary con, however, of DP is it is really simple but hard to grasp. We generally have a DP problem on the final. Final alert, learn some dynamic programming. You're going to have to write a DP solution on the final. Why is that relevant? Because as I say, it's difficult to grasp. DP problems are pretty hard to grade on the exam because the way that a DP solution works is you're trying to find sort of like the magical oomph in the problem. You need to find this recurrence relation and how to express that. Once you do that, your solution is generally 6 or 7 lines away. But before you've got that recurrence relation identified, your solution is absolutely 0 points. So it's a kind of a high-risk problem just because that's the way that dynamic programming works. You don't get it, and you don't get it, and you don't get it until you do, and then it's done. So that's what's one of the cons about DP is until you can really discover what that is, you've got nothing. And the way that I like to do my DP solutions is just jump somewhere in the middle. It's often easier because getting to those boundary cases can be a problem. So you say, well, how do I do this after 5 tries? Well, to know how I would do after 5 tries, I might check what I did for 4 tries or 3 tries and see which one of those makes my best 5 try. And we'll get into DP in a future lecture. But that's kind of what I say. And rather than figuring out, well, how do I start at 0 and then how do I go to 1 and how do I go to 2? Oftentimes for me, I find like sort of jumping into the middle and just imagining that recursion is already happening. I can sort of move forward and backward to say, well, if I know 5, it's easy to make 6. Or if I wanted to know 5, what did I need to know from before? Did I need to know 4 or did I need to know 4 and 3 and do some combination of those two? So the cons making this difficult to grasp are real. I try to tell people that, you know, like the first 3 times you learn dynamic programming, it's amazing because you'll learn DP and someone will say, here's a DP solution. You watch, you're like, oh yeah, I got that. Oh, okay, that's good. Now here's a DP problem for you to do. And nothing. You're like, wait a minute. I thought I understood this. Okay. And then you have someone show you the solution to the problem. Oh, yeah, that was easy. That was straightforward. That was DP. I get it. Okay, great. So I learned it once, and then I learned it again. Okay, now here's a new problem. DP it. And you sit there, and you don't get the recurrence. And nothing. And you have to go back and learn DP again. It's not hard to learn, but it's such a contrary method to the way that we do most of our physical things in life that our brains don't usually grasp it at the first one or two or maybe even three learnings of it. And then, you take some time off and you come back a semester or two after 281 and you're getting ready to go do your programming interview and you're like, there's going to be some DP problems on there. You better study it, because I promise you, after you've learned it, shortly after you've learned dynamic programming, you can almost always count on forgetting dynamic programming. So be aware that dynamic programming is its whole challenge. We'll be talking about that next week. But here's my example of why DP would be used. So I'm going to look at Fibonacci, and I can take something simple like, not simple, it's a really large number. Fibonacci of 50, right? And we know that Fibonacci of 50 is just fib of 49 plus fib of 48. Great. How do I calculate fib of 49? Well, that's just fib of 48 plus fib of 47. And fib of 48 is just fib of 47 plus fib of 46. And I can keep going on this, and you can see how this is really a tall tree that I'm going to be building up here. Fib of 46 plus fib of 46 plus fib of 45. And I'll do the same thing here. That's 46 plus fib of 45. And fib of 46, I can get that by saying fib of 45 plus fib of 44. All right, I've run out of room, definitely horizontally, and you're certain that I will run out of room vertically if I try to get all the way down to 0. But this is me taking a problem, Fibonacci 50, and dividing that into smaller problems that look like it, Fibonacci of 49 and Fibonacci of 48, right? So then, as I look at what I'm talking about when I'm saying these overlapping solutions, it looks like I need Fibonacci of 46 here, here, and here, because there's some overlap between how I solve Fibonacci of 48 and how I solve Fibonacci of 47. They both require Fibonacci of 46. That's why I say that these two subproblems are not independent. They're related. They've got some overlap in them. So this is the type of problem that would require a DP solution, one that has overlapping subproblems. And as I go through this, you see that there's a couple of copies of 45, 45, and 45. And as I go to the next level, I'll be needing more and more overlaps and more and more and more overlaps and more and more and more and more and more overlaps. It goes and goes and goes, and it gets pretty exponential looking. But if you say, well, if I solve this once, then when it comes up again and again, and I don't do any work, I can get that answer in a constant amount of time, then it changes the complexity of how this works. So that's what DP does, and as I mentioned, we'll get into this more in the future. A whole lecture on DP Monday. Types of algorithm problems. All right, we've moved past our subdivided solution sets. Right now we're looking at the last two families, backtracking and branch and bound. And to understand where those algorithm families come from, I need to understand where their problems come from, right? So the two types of problem I'm going to be looking at are, first of all, constraint satisfaction problems. So a constraint satisfaction problem is straightforward. It says, can we come up with a solution that satisfies all the constraints? So we already talked about giving change. Our primary, there's one constraint there. Did I give the right amount of change? So that's all that really matters for making people happy. Like, did you get your money back? And did your boss, you didn't give more money than you should? So that's the constraint to be satisfied in the constraint satisfaction problem. There may be more than one solution, right? Because if I'm not talking about optimal change, I can give you 3 dimes, I can give you a quarter and 5 pennies, I can give you 25 pennies and a nickel, and so on. All of them are solutions because the constraint of making the correct amount of change has been satisfied. Other examples of constraint satisfaction problem are sorting, getting through a maze, spanning tree, not a minimum spanning tree, just a spanning tree. Is there a way that I can connect all of these locations? Is there a highway between this city and that city? Then I can say that there is a highway, a spanning tree highway from everywhere. All right, so those are constraint satisfaction problems. They just say, I've got some rules and I need to find a solution that doesn't break any rules. An optimization problem is one where we're obviously trying to get some minimization or maximization. We're trying to find the most we can gain or the least we can spend. So those are how optimization problems work. But hidden in an optimization problem is also a constraint satisfaction problem. Because if I say, well, here's the shortest distance from A to C, well, that wasn't the constraint. The constraint was I was trying to go from A to B. You giving me a solution from A to C is not useful. I gather that it's optimal. It's the optimal travel from A to C, but it hasn't solved the problem, which is getting me from A to B. So there is a constraint satisfaction problem hidden underneath every optimization problem. Say, is there a legal way to get a solution, and is it the most optimal? Is it the cheapest, or is it the one that gains the most? So examples there can also be giving change with a minimum number of coins now, like giving correct change, I should say. An MST, which is now a minimal spanning tree or minimum spanning tree, however you spell that. If you look at a spanning tree that just makes sure we're all connected, that's great. There's a bunch of those, but what I want is the one that has the least amount of weight when it's done. So that's an optimization, because the underlying constraint satisfaction problem is everything connected? And then the optimization portion of it is, have I done it as cheaply as possible? So those are 2 types of problems, and we're going to find out how to solve them, right? I can say a constraint satisfaction problem, usually I'm just looking for, is there a way to do this? If there's a way to do this, I just want to report that I can solve this problem. Is there a way to get out of this maze? Yes, there is. That's all I needed to know, because I'm not stuck in the maze anymore. Right? You don't go back in and say, well, let me see all the ways out of this maze. Usually a constraint satisfaction problem can stop when a satisfying solution is found. Optimization problems, usually you can't stop early. It's almost impossible to, because once you found a solution, something that hasn't violated any constraints, you say, well, this one cost me 7. Great. What does that mean in relationship to all of the others? I don't know. If I've only ever found one solution and it's 7, I'm not certain that there isn't a better solution that costs 6, or a better solution that costs 3, for instance. Until I've found all of the possible solutions, it's hard to say that I know for sure what the best possible solution is. So you end up developing this set of possible solutions. We call this a feasibility set. And then as I apply this objective function, that's the one that's going to say, how am I going to pick the best solution out of the feasibility set? Enter our 2 new families. Constraint satisfaction problems can sometimes be solved with their own specialized algorithm, but any constraint satisfaction problem can always rely on a basic backtracking algorithm to solve it. You can fall back on that, fall back on a more generalized solution. The same thing is true with an optimization problem. There may be a particular way to solve any problem in particular, but in general, if it's an optimization problem, I can use a branch and bound algorithm to solve it as well. So that's what it says here in my bottom bullet. For a particular problem, there may be much more efficient approaches, but these are fallbacks, like to a more sophisticated version of a brute force approach, right? And you say, brute force? I thought we were past that. Well, listen to this definition. Backtracking algorithms systematically consider all possible outcomes of each decision, but prune searches that don't satisfy the constraints. So that first part of the sentence, systematically consider all possible outcomes of each decision. That sounds like brute force. And in truth, backtracking algorithms have the same worst case complexity as brute force algorithms because you will check everything. Why is backtracking better than brute force? That's second part of the sentence. But prune searches that don't satisfy our constraints. So what this means is, as I'm going through my change drawer, in a brute force method, I can say I'm trying to make 30 cents change. And I've got this whole pile of quarters, whole pile of dimes, whole pile of nickels, and so on. And say, well, what if I put a quarter in there? Okay, that's still a good start. What if I put 2 quarters in there? Well, that's made more than 30 cents change, but brute force wouldn't care, because brute force would say, well, what if I put 3 quarters in there? What if I put 4 quarters in there? What if I put 15 quarters in there? Right? Brute force tries every possible combination, where backtracking is going to prune. It's going to say, once I've violated a constraint, don't go any farther. So once I've tried 2 quarters to make 30 cents, backtracking and say, well, that's a fail. There's no need to try 3. There's no need to try 4. There's no need to try 5. So I've considered all of them, but I can use this broad sweeping constraint failure to say, well, if 2 fails, then anything from 2 to 400 and off to infinity is going to fail. So I don't have to check those. Whereas brute force checks as many coins as you have in the drawer, no matter what. So they sound similar. This systematically consider all possible outcomes of each decision. But because of pruning in backtracking, I end up with something that's a lot better. And it's much harder to say what that is going to be in terms of complexity. It's very specific to each case and very complicated. So in the end, we think of backtracking still as having the same complexity as brute force, but it's always faster, right? So we can look at that. I guess it's not always faster, but generally it's faster. As we look at it, we say we're going to eliminate the exhaustive search. So it is going to be faster than brute force, because I said consider all possible outcomes. That doesn't mean I have to do an exhaustive search, right? That pruning prevents the exhaustive search. So even though it has the same worst case complexity, we end up with something that's faster. The cons are we still end up with a fairly large search space. Let's look at our first applied constraint satisfaction. We'll talk about backtracking with four-coloring. And this example is how I can color a graph with 4 colors. And what I mean is to assign a color to each vertex and then have it in such a way that no 2 vertices that are adjacent, so that means that there's an edge between the 2 vertexes, then they're adjacent. So no 2 adjacent vertices can be the same color. That's what I'm looking for in a graph coloring. Some graphs can be 4-colored and some can't. I'll let you think about which graphs can or can't be. So then my question is, given a graph, is it 4-colorable? Well, let's start out with which graphs can and which graphs can't. Well, if it's less than 4 vertices, then obviously I can 4-color it, because with one item I color it one color and there's no adjacency problems. With 2 items, regardless of how adjacent they are, as long as they're different colors, is no problem. 3 items, 4 items, no matter what the adjacencies are, I can always just color something a different color. Now, what happens when I get to 5? If I've got any sort of disconnect, so some node or nodes that cannot be reached from other node or nodes, then clearly that just really turns it into a 4 and 1 or a 3 and 2 or something along those lines, that I could independently color those things with the 4 colors and have no problem. So if it's disconnected and it's 5, I absolutely can. If there's not a click, which is a graph definition, and in a click, that's a graph in which every pair of vertices is connected by an edge. So in a click, we can think of that as a fully connected graph. Obviously, if I've only got 4 colors and 5 nodes, I cannot four-color that because everything is next to everything else. Right? If there's not a click, then I can with 5 because there's somebody that's not connected to somebody else. And we can figure out a way to get our coloring in there that eventually works. Once I get up to n equals 6 nodes or 6 vertices, there's no simple answer. Those from 5 and below, those are pretty easy. However, once I get to 6, I end up with a problem that's actually very hard to solve. And this type of problem is called NP-complete. So an NP-complete problem, we can say that we don't have a polynomial solution. So there's no polynomial solution to this. I may be able to take a solution that's offered and verify that it's a good solution in polynomial time, but I can't generate the solution in polynomial time. So once we get above 6, this is a very complicated problem. Here's an example of graph coloring. Looks like map coloring. But we know that a map can be represented by a graph. With each one of my states, here in the United States map, each one of my states is a vertex, and every border, a line between two states, is an edge. And that's represented by something like that. So look in the southeast corner, right? Here's the southeast corner. That's Florida. And we can see just this section of it. If I look at each one of those locations and sort of say, well, here's Georgia, and since there's a border between Florida and Georgia, I might draw this as Georgia connected to Florida, right? And this is Tennessee here, and you can see that there's also some border between Tennessee and Georgia. So there would be an edge between Tennessee and Georgia. But since Tennessee and Florida have no edge, there's no sort of line that would connect this vertex to that vertex. That's great. So maps can be drawn as planar graphs. So a planar graph is a graph that can be drawn with no crossing edges. That's important. Conversion to a map of a map to a planar graph is pretty straightforward. I mentioned states become nodes, shared borders become edges, and then I've got a planar graph. So anything that I can physically represent on a cartographic map, I can say that I can draw that as a planar graph. That's a fun one. And anything that I draw with crisscrossing lines, then I cannot draw as a map that I would put on the wall. So here's that small segment of the U.S. again, the southeast corner there, and what this might look like in a map to graph conversion. So you see each one of my states. I've got Mississippi here, Alabama, here's Tennessee, this is North Carolina, South Carolina, Georgia, and Florida. So given that, you can see how I can take this and make that. Here's physical, here's logical. All right, so using 4 colors, I'm going to try to convert this. And I'm going to start maybe from the left here. Let's start at Mississippi, like we read left to right. And every time I get to a new location, I'm just going to rotate through a new color. Red, then blue, then green, then orange. So if I mark Mississippi as red, and then I go to Tennessee and mark that as blue, I'm doing well so far. I'm keep moving east here. I'll call this green. I'll work my way back around to the south. So what happens? I'm going to take and mark South Carolina as orange. All right, Georgia's next. If I try to mark Georgia as red, I'm okay there. Right? Now, when I try to mark Alabama as blue, oops, that's not very blue, is it? You see I've violated a constraint here because I've got 2 states, Tennessee and Alabama, that have a border. There's an edge between these 2 nodes, and if they're the same color, then my graph coloring is not workable. So what do? I backtrack. I say, well, let's not make that one blue. What if I make that one green? Green works, right? And then I keep going through that color cycle, and I say, can I make Florida orange? And Florida loves that. They love oranges. There we go. So there is a legal graph coloring. You can see that all of my states have a color associated, and none of them are adjacent to a state that is the same color. So that's one way to do it. And I got there with a simple backtrack. I tried to color something. It violated a constraint. I went back and I picked another color there. And that was a simple sort of there was one misstep in there. But in a true backtracking algorithm, I might end up going all the way back to the initial coloring and saying, maybe there's no way that I can do this whole map with the first one as red. So this is a version of it. And you see there's multiple versions of it. So my version had Florida as orange. It could also be blue, but everything else in here was the same there. And that's fine, right? Now, can I do this with 3 colors? Can I 3-color this? Well, if I start out here, let's just get something I can move fast with, right? Let's make this red, now blue, and green. Okay, and then I keep going here. Red is legal there. And I try to color Georgia blue, which violates a constraint. So I have to not make this blue. Red, blue. What about if I make it green? All right. Well, green violates this constraint. So I can't make it green. I can't make it blue. I can't make it red. All right? Because if I were to try to make it red, it's already obviously next to South Carolina here. So making it red would violate that constraint. So with what I've got so far, red, blue, green, red, there's no way to solve this, right? There's no way to 3-color this. So let's backtrack. Backtracking said the last choice you made, unmake that choice and make another. So to backtrack, what I'm going to do is I'm going to say red was a bad choice here. So let's try blue. Blue starts out all right, because now I can color Georgia red. There's nothing that is adjacent to that's violating any constraints. I can come down and color Alabama blue. Wait, that violates a constraint across here. So I'm not going to take blue there. What if I made it green? That looks legal. And can I put a red here? Because I keep going red, blue, green, red, blue, green, red, blue, green. Well, that violates a constraint. So let's make this blue. And there I have a 3-coloring. And you see how backtracking lets me make a choice. When it violates a constraint, I back up and remake that choice. So there we have it. So from enumeration to backtracking. Enumeration is for every vertex, I'm going to take that vertex and consider that it has 4 colors. And these 4 colors look like 4 branches in a decision tree. If I make this node red, then after that, I've got a choice to make the next nodes whatever color they are. But every time I make a decision, I sort of get a set of branches that go below that decision. So if I've got some edge between 2 vertices, then I end up with some dead ends, right? Because if V1 is next to V2, I know that since each vertex can have 4 colors, I should have 16 different choices there. But since they're adjacent, I can't color them both red, can't color them both blue, can't color them both green, and so on. So there's 4 dead ends if V1 and V2 are adjacent, because once I've colored one red and the next one next to it red, the entire rest of my search is invalid because I've violated a constraint. So those dead ends won't lead to a solution, and I get to prune that stuff out of there, which is really pretty nice. So here's backtracking. We branch on every possibility, and we sort of maintain these partial solutions. And we maintain them generally in our call stack. I've worked my way through this thing, or I can maintain it in a data structure where I mark and unmark possible choices. And so I've got this one or more partial solutions. As I try to extend the solution closer to a full solution, when I make a mistake, I backtrack. I say, okay, well, if I violated a constraint because I made this choice, try making another choice. If I end up in a situation where I've tried all of the choices for a particular node and they all fail, then I back up to the node before that and say, well, what if I made a different choice at this node? And you keep backtracking that way. So if for instance, I've colored 7 states in and there's no way to color the 7th state, say, well, what if I back up and try the 6th state, a new color? Haven't violated any constraints. Now I try the 7th state again. Well, if that fails again, I go back to the 6th state, try a new color. If I get to the situation where I've violated constraints, no matter what, I can never place a 7th state with the placement of any 6th state, then I backtrack even further and say, well, maybe if I made a different choice at the 5th state, I can make a better 6th state choice that would eventually get me to a legal 7th state choice. So that's how backtracking works, and you can get all the way back to the very beginning. We'll have a lecture on backtracking, branch and bound as well. Today we're just talking about the family to make this understood. So we say, why is this better than sum enumeration? Well, when I find those dead ends, I come up with some really cool optimization here, right? So imagine I'm trying to make some decisions here, and I'm trying to 4-color these states, right? And what do we look at? We looked at something that had 7 states. So as I look at 7 states, I can say my first decision to color V1, that first state, I could go 4 ways with that. And then below that, since each one of those can be 4 different colors, I end up with a tree that looks like this. My decision tree, right? And so this might say, I'll color V1 red, and here I'll say I'll cover RGBO. So now I've got that. And so each one of these marks something similar. RGBO, RGBO. And these are all my decisions that I'm making at V2. So in order for me to color the entire subsection here, I'm going to end up with, 4 coming off of this red. That's a 5er. 4 coming off of this red. I've got 4 coming off of this green, 4 coming off of this blue, 4 coming off this orange, and so on. So every level I go down, I multiply by my total number of options by 4. But if I can say that V1 and V2 are adjacent, if I've colored V1 red, I cannot color V2 red as well. So this entire subtree then gets invalidated because I've got a constraint violation, right? And there's another one in here when I color the first one green and the second one green. Because they're adjacent, this gets cut out. And the blue V blue gets cut out. And so I've got this violated constraint, and because I violated a constraint early, I ended up cutting out 25% of all of what was remaining. So that's why we say this is better than enumeration. Enumeration is really what brute force does. Enumeration looks at everyone. We're not trying to look at everyone. We're trying to systematically consider them. And I can do that by saying, I know that a violated constraint anywhere higher up in this tree is going to prevent me from needing to look any lower. So here's a nice pseudocode algorithm of M coloring. We see that we've got this input as the number of nodes N, the number of colors M, and I'm also coming with some adjacency matrix that shows me which of my N nodes are adjacent to which other N nodes. So I can say that in W, at I and J, I've got true if there's an edge that connects vertex I and vertex J. Otherwise, it's false. That's my input. Excuse me. My output is going to be all possible colorings of a graph represented by this integer colorings, right? This vector of the color for each one of the N nodes. All right? So here's the algorithm. It's pretty straightforward. It's just a few lines. But it's a little tricky there, though. If promising of I, that's what's not here. So if promising of I, we'll show you that in a minute, though. So I've just decided to color sort of this index I, and so I'm saying, well, we've just tried to color the first state. Can we extend the solution any further? So, well, first we got to see if the color that we applied to this state is promising, right? Because if it's promising, then that means I haven't violated any constraints. So if I've got my first state in there, it's always going to be promising. Once I've got the second state in there, if it's adjacent to the first state and it's the same color as the first state, this is not promising. This is a violated constraint, so there's no need to try to extend this any further. You see that M coloring is my function. It's going to call M coloring again later. So yes, we've got recursion going on here. And my base case is going to let me fall out right here is say, well, if you're trying to color all of these states, right, every time I color a new state, I say, well, I've colored state 1, I've colored state 2, I've colored state 3. And I get into this, that's my base case. I say, well, if you've colored all the states, then stop. So N is the number of states, and I is the state that we've just colored, the number of states that we've just colored. So if the number of states I've colored is equal to the total number of states, and it's promising, then I can print that out because it hasn't violated any constraints, and it's got all the states colored. So print that. So there's my solution find. If I'm promising, that means I haven't violated any constraints, but I'm not done, means I is not equal to N, then I fall into this else. And what this else is attempting to do is just trying to extend the solution. You say, well, you're trying to color 7 states, and currently you've got 4. Let's see if we can make that 4 look like 5. And what we do is loop through all of the options that I might color a particular state and try that next state in that color and say, now I've extended this. It goes back, recurses back in and say, we've just extended it. Is it promising? Has it violated any constraints? Because if it's violated any constraints, it's not promising. We'll return from this and it'll put us right back inside of this for loop from the previous call. So this one is another one of those challenging ones that's going to throw us a curve because not only does it involve recursion, but it involves recursion inside of iteration. So these are pretty challenging to figure out. Like I said, I like to approach these from the middle and say, while I'm coloring 4, right? While I'm coloring 4, I'm trying to figure out how I can color 5. And when 5 fails repeatedly, 4 goes back because it was called from inside at 3. And so on. So make sure you've understood this because we've got a big algorithm coming up here in Project 4 that works very similar to this. You're going to have to make sure you understand this. Here's promising as promised. So in this particular application, I say promising means I've just colored index I. Let's start at the beginning, j equal to 1. And say the switch is true, meaning this is going to be promising unless I find something that proves otherwise. So I'm trying to get to I starting from the beginning. So I look at everything. So for every j less than I, if I and j are adjacent and they're the same color, then this is a bad thing. I set the switch to false, which will also get me out of my while loop. And once it's false, I get out of the while loop. I return false. But if I go through all from j all the way up to I, and I find that every node that's been colored is not the same color or not adjacent, right? That's where we fail. If it's not adjacent, I don't care. If these two nodes, I and j, aren't adjacent, I don't care. But if they are adjacent and they're not the same color, I keep moving, right? It's only when they're adjacent and the same color that I get out. Otherwise, I just increment j. So this is promising. And every time you write a promising function, it's going to be very specific to the constraint satisfaction problem you're solving. So that's where the challenge of backtracking is. All of our backtracking algorithms are going to take a similar form to this M coloring that we see here, because the only thing that's unique about this is how do I figure out whether I haven't violated any constraints? That's where promising comes in. So you can look at this and work your way through trying to do M coloring with this algorithm. I strongly suggest you do it. give each one of these states a number that you like. And we've already seen the ones that we've worked with. How about something a little bit more complicated, like let's start here at, and this pseudocode is all one indexed. So let's say this is index 1. There's 2, 3, 4, 5, 6, and 7. So take that in your time studying or working through this and try to apply M coloring. And when you try to figure out what you've done, see if promising lets that work with this particular numbering. Try a different numbering, try a different number of colors, see if you can 3-color this thing with that algorithm, with that start, see how promising works, see how M coloring works, see how backtracking works. When is backtracking efficient? Well, it's got this constraint violation thing that lets me cut out large portions of this search space, right? Doesn't necessarily improve the asymptotic complexity, because we saw that if I cut out 25% of my, after my first 2 choices, I could cut out 25% of my search tree, because red next to red is bad, green next to green is bad, blue next to blue is bad, and so on. So it lets me cut out 25%, but what I end up with is something like I had some complexity, and if I was big O of X, now I'm looking at being big O of 0.25x, just, or 0.75, just because I cut out 25%, it's still big O of X, right, in my worst case scenario. And even worse, right, if I get down to something that's like, I'm reducing 99% of this stuff, and so every time I go to a new level, I've still only got 1% of that, it still ends up as a big O of b to the n here. So I haven't really changed my overall asymptotic complexity, but it does end up a lot faster. If every time I'm making 1% of the work, it's a lot faster. So this works great because when I've got highly constrained problems, the constraint violations happen all the time, and I'm able to prune more. And I can backtrack more quickly and say, okay, well, instead of making 15 decisions and realizing that my second decision was bad, because I've violated constraints early, I can get out after 2 decisions or 3 decisions and prune backwards. So it works when I've got a highly constrained problem. It also works when I've got a lowly constrained or under-constrained problem, because with minimal constraints, it's easy to just pick a good solution. That's good, that's good, that's good. You got no problem with that? Oh, wait, I'm done? Easy. So in a highly constrained or under-constrained problem, backtracking is really efficient. All right, if you're paying attention, you'll notice I'm rounding up here. I'm on a summary slide, and I did not mention branch and bound. Branch and bound is an extension of backtracking, and it's got its own lecture coming up as well. But I'll give you the executive summary on branch and bound. Branch and bound can be thought of like a constraint satisfaction problem. We already said that. So I've got this constraint satisfaction problem. I can backtrack my way into solving something branch and bound. And I would eventually get there because I would have to find them all and find the smallest one. But what branch and bound does is it adds one more constraint. Because in branch and bound, we're trying to optimize. So we've got all of the constraints that the problem gives us, like don't make too much change, or don't color 2 states next to each other, or whatever the problem is. Those constraints still hold, but then branch and bound says, I'm going to apply an additional constraint that says I'm looking for an optimal solution. And once I've found an optimal solution, or possibly optimal solution, once I've found any solution, then as I look at finding other solutions, the new solutions have to do 2 things. They have to, one, now not violate any constraints that I previously had on the problem, but they also have to appear to be more efficient. So if I've got a solution that's a probable solution, then as I'm looking for my next solution, if I have something that hasn't even violated a constraint, but it isn't going to be more efficient, more optimal, be cheaper or more winsome or whatever your metric is, if it's not going to be a better solution, then I add this new sort of metric constraint. Say, well, I haven't violated any of the rules, but this one doesn't look like it's going to be better, and since I'm looking for the best, I'm able to prune that as well. So we'll go into branch and bound, as I mentioned, in a full lecture all by itself. Here, that's in the coming days. But we'll look into that. So here's our summary. We talked about brute force, solve the problem in the simplest way, generate the entire solution set, pick the best. It will always give us an optimal solution. Typically, though, it's not very good at being efficient to getting that done. But because it checks everything, brute force will always, always, always find the optimal solution. Greedy makes these local optimal choices. The best decision I can make at the time. Don't look forward, don't look back. Just take the best right now. This may give an optimal solution, typically better efficiency than brute force, but some of them might not. It depends on this greedy optimality property, right? If I make a choice that's the best now, but it prevents me from making a better choice in the future, then I've violated the greedy optimality principle, and I end up with a solution that is not globally optimal. Even though it's a collection of best decisions at the time, when you add it all up, you might not have that. And you can think of that as like, if I'm trying to connect a bunch of points, and I say, well, this one's closer, so I'll go to that one. I go to this one, that one. I go to this one, I get all the way to the very end, and now there's one point that's really far away that could have been more easily joined earlier just by taking something a little less optimal, right? So that's the sort of thing that violates the greedy optimality principle, right? Making the best decision now prevents me from making a better decision in the future. Divide and conquer and dynamic programming, those are my two sub-problem solution families. D and Q, we divided into non-overlapping subspaces, thinking binary search, thinking quicksort. Dynamic programming, I've got these overlapping subspaces. We'll talk about more of them. Use that when the partial solution, I'm going to use that later. Oftentimes, looking nearby for a previously calculated value is a lot cheaper than calculating the value from the ground up. Backtracking and branch and bound. Here are my constraint satisfiers, and then constraint satisfying with optimization in branch and bound. Both of them do some pruning, and we get rid of these non-promising branches. And that saves our what looks like would be an exhaustive search from being really that bad. All right, P4 is upon us, so here's the first round of tips and tricks. There's tutorial slides, there's video. Watch that stuff. It's going to make a difference. In the project, the vertices are numbers in the range from 0 to V as we read those in, and that's a 0 to V inclusive, exclusive. So it's really easy to index things. As we read them in from the file, you're just going to be getting coordinates, and the first coordinate in the file, that's vertex 0. The second coordinate in the file, that's vertex 1, and so on. MST, that is part A, and fast TSP, that's part B, might have up to 50,000 vertices. So that's a large collection of vertices. But what's even larger than that is, since they're all connected, everything is connected to everything, if I was going to try to write a distance matrix or an adjacency matrix there, I'd have something that would take upwards of 20 gigabytes, and you won't be afforded that. So in parts A and B, you have to recalculate your distances. You can't come up with a distance matrix. OptTSP is a much more complicated problem to solve and far slower, so we're going to be keeping that to something that's shorter, right? 40 vertices at most. So now we look at 40 vertices. I say, can I put 40 times 40 or 1600 doubles together? Absolutely. If you want a distance matrix, you can do that. So in that way, rather than computing these distance v factorial times, I can calculate them v squared times and then just look them up v factorial times. So you can get some savings there if you want to work a distance matrix into your part C, but you can't distance matrix parts A and B. So part A is going to give us MST, which we've already covered. Part B is going to be fast TSP. And fast TSP is an estimation. Fast TSP is not going to always give you the optimal solution. Many times it won't. But it's going to be much faster to calculate than optimal solution. And so in order for you to pull that one off, you're going to have to go do some internet research there. Learn about some fast TSP heuristics and implement one or two or however many of them it takes for you to get that down. Right? Then opt TSP, we're going to solve with branch and bound. And we'll talk about branch and bound in tomorrow's lecture. And we'll talk about backtracking some more then as well. So we'll get some more on that. If those seemed a little hazy to you, don't worry, they are coming really quickly. But start with part A, because you can use your part A solution to help you with part C. And part A is already straightforward. It's something we've already discussed in lecture. We've done Prim's algorithm. We've done Kruskal's algorithm. Hint, you're going to use Prim's. And you're going to do MST and make a solution for it. The TSP slides, Traveling Salesperson Program, the Traveling Salesperson Problem, has code that's going to help you with OptTSP. The function is genperms. You're going to use it. It's also in a text file on Canvas. The reason we put it there is every time we say, don't copy this out of a PDF, people copy it out of a PDF because they don't want to type in a 7 or 8 line program. And it's much easier to copy and paste that. But PDF contains invisible characters that invariably break code. So don't copy out of a PDF if you're going to be using that in code. So we've got it in a file. You can grab that. The graph that you're going to be given is what we call a connected graph. And in parts B and C, the entire map is going to be a click. The entire graph is going to be a click. Every point is going to be connected to every other point in parts B and C. In part A, it's not quite completely connected. We've got sort of this medical campus and the normal campus. Or if we're doing Pokemon, we're doing water Pokemon versus land Pokemon. Or if we're doing donuts, we're doing American donut shops versus Canadian donut shops. But in the MST part A, we've got this concept of a border that divides part of the two-dimensional plane, and we talk about things inside one section can't be reached directly by things outside that section. The graph is still fully connected because we'll have nodes on the border, and a node on the border can connect to anything on either side of the border. But without a border crossing, whether that's from campus to campus or country to country or terrain type to terrain type, you can't go directly from water to land. You have to go water to beach to land, land to beach to water, no problem, land to land, no problem, beach to beach, no problem, and also beach to land and beach to water, no problem. But there's a problem when you try to go from water to land. And that's the same thing with our campuses as well. You have to go through a border between campuses, or when you're trying to cross between the country, you can't go directly from Detroit to Toronto. You have to cross at the border. So that's going to be the way that the MST or Part A works. For fast TSP and OptTSP, I mentioned the graph is completely connected. And then if we look at this, we say that since everything is all connected, even in the MST, the stuff inside one segment is fully connected and the stuff inside the other segment is fully connected. So now we're trying to decide, is this a dense graph or is this a sparse graph? That is where I will leave you.